Hello, everyone. Welcome to the Math Magician's Den. This is the Herm Dog. We're here again today to talk about derivatives, and this time we're going to talk about a certain application. We're going to talk about rates of change with respect to a projectile, and the projectile we're going to talk about is this: a projectile that basically goes straight up and then straight down. Okay? We can't talk about projectiles that go at an angle because then we got to talk about trig as well. Let's keep it simple today. We're going to talk about projectiles that go straight up and straight down. And this is the basic equation we're going to end up with in every single case. Okay? 1/2 of g, and what is g? Ladies and gentlemen, g is gravity. And gravity, since we live in America where I'm filming this video, we have to talk about standard units. Gravity is negative because it pulls things down 32 feet per second squared. That's an acceleration. Okay? Gravity, when we're talking about the metric system, which is used pretty much everywhere around the world, is negative 9.8 meters per second squared. So that's the force of gravity. Okay? Now, in the book that I use, in a lot of the books that I've looked at, they use S as a position. Some books will use height of the projectile. This book happens to use S for position of the projectile. So this is the position of the projectile. Like I said, some books will say height, h of t. V is the velocity. And when we talk about velocity, we're talking about the velocity right now. We're not talking about average velocity. That's something different. Average velocity is the change in position over change in time, or the change in the height over the change in the time. That's more like a secant line, whereas the velocity I'm talking about is more like a tangent line. An average velocity would be something like this. Let's say you took a 300-mile trip and you completed that 300-mile trip in 6 hours. Well, 300 divided by 6, that's 50 miles per hour. That's an average velocity. If you looked at your speedometer in your car while you're making that trip and you see, hey, I'm going 50 miles per hour right now, that's an instantaneous velocity. And we're obviously going to let t be time. And here, time, we're just going to use hours at first. And let's talk about the difference between speed and velocity. Speed is essentially velocity without a direction. So we talk about how fast my car is going. It's going 50 miles per hour to work. I'm driving 50 miles per hour back from work. I don't say negative 50 miles per hour. So speed, you think of velocity without a direction. Now we have some other notations here that I need to talk about. And these are essentially initial position. When you see S sub 0, you're talking about the position at time t equals 0. When you see initial velocity, V sub 0, that's the velocity at time 0. Delta t is the change in time. Okay. Delta x is the change in position. And I tell you what, we're not even going to use this for this video. Okay. Because if I use that for this video, okay, I'm just going to make my life even harder. So we're going to do a couple examples here of position, velocity, acceleration. Now, I'm using an example that basically deals with Columbus, Ohio, where I'm from. There is a building in Columbus, Ohio that's called the Rhodes State Office Tower, and it is 629 feet high. Let's say I dropped a coin from the height at the top of that Rhodes Tower. How would you determine your position, your velocity functions for the coin? Well, here's what we're going to do. First of all, to write a position function, we have to take half of gravity. Well, gravity, since I'm talking about feet, would be negative 32, and that would be multiplied by t squared. Now, when you look at the equation in the previous screen, it's the initial velocity next. Well, the initial velocity, if I drop it, is 0 times t. And then the initial height would be 629 feet. So your position function for this particular coin would be negative 16 t squared plus 629. That is my position function. Now, how am I supposed to find my velocity function? My velocity function is instantaneous velocity. We're going to take the derivative. The derivative of the position function will be your velocity function. So what's the derivative of negative 16t squared? You would bring the 2 out front and multiply, so it would be negative 32. And t would now be raised to the first. And what's the derivative of the 629? Well, that would be 0. So this is my velocity function. And I found it because it's the derivative of my position function. Now, if I want to find the average velocity on this interval, the average velocity is found by taking the change in the position between 2 seconds and 1 second over the change in time, 2 seconds minus 1 second. So it's change in position over change in time. Well, if we plug in 2 to my position equation, and I'm going to use my calculator real quick to do that. If I plug in negative 16 times 2 squared plus 629, I'm going to get 565. Okay? And I'm going to subtract s of 1. And I'm going to do the same thing. I'm going to plug 1 into the position equation, and I come out with 613. This is obviously all over 1. And if I subtract those two numbers on the top, I actually get negative 48. And since this is a velocity, I would say feet per second. Get used to putting your units on these problems, because what's going to happen is on an AP exam, they would expect the units for you to get full credit. Now, when I asked for the instantaneous velocities at t equals 1 and t equals 2, you notice I didn't say over an interval. I said at a specific time. What's the velocity at 1? Well, that's negative 32 times 1. When I say instantaneous, that's the derivative. That's the velocity, not the average velocity, the instantaneous velocity. It would be negative 32 feet per second. And then I can say, well, what's the velocity at 2 seconds? I would take negative 32 times 2 because I'm using this velocity function. This would be negative 64 feet per second. Why is it increasing? Well, increasing negatively. It's because of gravity. Every second it's making it go 32 feet per second faster. Now, what's the time it takes for this projectile to hit the ground? Well, when you're hitting the ground, what is that? When you're hitting the ground, that's a position. So I want to take my negative 16 t squared plus 629, and I want to set that equal to 0. Now, if I do some solving here, I get t squared equals, you would subtract the 629, you would divide by negative 16, and you would take a square root. Okay? So again, I'm using my calculator, and I come out with 6.269 and a bunch of zeros. And usually on the AP exam, they say you can either truncate, which is 629 or 6.269 seconds, or we can say 6.270 seconds. That's how long it takes to hit the ground. Okay? That's the time that's required for it to hit the ground. Now, what's the velocity at impact? The velocity at impact, we have to plug that number that I just found, that's 6.269, yada, 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 into my velocity function. And I'm telling you, don't ever plug a rounded number into another function to find your answer. Sometimes you can be off a little bit. So on my calculator, I'm going to take negative 32 times that answer that I just found, and I get negative 200. And if I truncate, it's 638. And truncate means just chop the decimal off. If I round, it's 639. And what would this be? Okay. This would be feet per second. Now, when you talk about feet per second, how fast is that? Well, in our case, negative 200.639, if I convert that to miles per hour, okay, I'm going to multiply by 3,600, and I'm going to divide by 5,280. This is actually negative 136.799 miles per hour. I don't think I'd want to get hit by that coin. That's pretty fast. And it's just dropping 629 feet. And of course, this is not thinking about air resistance. Now let's do a similar question based on meters, metric. This time when I write my position function, okay, I'm going to have to take half of the force of gravity, which is negative 9.8 in the metric system, times t squared. I have to add my velocity times the time. Now, if a projectile is shot up from the surface of the Earth with an initial velocity of 150 meters per second, first of all, it's going up, so the velocity should be positive. And if it's going up, it should be positive 150 meters per second. So it's 150 times t. And the initial velocity, the initial position is the ground, so we're saying 0. So this comes out to be negative 4.9 t squared plus 150 t. That, ladies and gentlemen, is my position function. Now, how do I find my velocity function? Well, my velocity function is, again, found by taking the derivative of position. To find my velocity function, bring the 2 out front, and that would be negative 9.8 t. Take the derivative of 150 t, and you just get 150. There is my velocity function. Now, again, when it comes to velocities, this is an instantaneous velocity function. Average velocity, again, if they ever ask for average velocity, that's change in position or change in height over change in time. But on this next problem, it asks for the velocity at 5 seconds. It asks for the velocity at 10 seconds. So I'm going to take this negative 9.8, and I'm going to multiply it by 5, and then add 150. This comes out to be 101, and this would be meters per second. Okay, so it's a positive velocity. It's going into the air. Now, if I plug in 10, okay, and I'm doing that right now, I'm going to get 52 meters per second. So when I went another 10 seconds, that projectile slowed down, but it's still going up into the air. Now, how many seconds will it take for this projectile to hit the ground? Now, remember, when you're hitting the ground, this is a position again. So I'm going to take the original position function, negative 4.9 t squared plus 150 t, and I'm going to set that equal to 0. Now, what I can do with my graphing calculator is I could actually set this function equal to my y1 in my graphing calculator. I could graph it and look for the x-intercepts. I could also do this. I could take out a negative t, and I'd be left with 4.9 t minus 150 equals 0. And if I set this t equal to 0, that's obviously when it took off. If I set this factor equal to 0, I get t equals 150 over 4.9. And 150 divided by 4.9 is about 30.612 seconds. It takes 30.612 seconds for that projectile to hit the ground again. So it went up, hit a maximum, came back down. Okay? Now, what was the velocity of the projectile when it hit the ground? I'm sure a lot of you have already figured this out. If it left the ground at 150 meters per second, and then it came down exactly opposite of what it went up, you would think it would be negative 150 meters per second. Well, let's find that out. All I'd have to do is take the velocity function, which is negative 9.8, and multiply it by this 30.612, and I would use the entire decimal, and then add 150. And when I do this on my graphing calculator, I do get negative 150 meters per second. Now, because it went straight up and straight down to the exact same point, when did it reach its highest point? Well, it reached its highest point at half of that number. It's at about 15.306 seconds is when it reached its highest point. So we could even figure out how high the projectile went as well. I hope this helps with some position and velocity. Remember, if you have a position function, the first derivative is its velocity. And if you like this video, please hit the like button. Be sure to subscribe. If you'd like to see more videos, I'll be posting more in the near future here.